For extremely complex problems, some computer calculations take a lot longer and are less refined than what scientists need. The work of three men may be moving us to something faster, a quantum computer. One of them is theoretical physicist Ignacio Cirac.
With a quantum computer would make this time shorter, so you can do the calculations faster.
He says a quantum computer would take advantage of the physics unique to the world of the very small.
So quantum mechanics is a theory that describes the microscopic world. The laws that we know are not valid for it, so they behave differently. They have different laws.
Cirac, David Wineland of the National Institute of Standards and Technology, and Peter Zoller of Innsbruck University have worked to harness the unique laws of quantum mechanics to bring us closer to a quantum computer, which would be far more powerful than anything available today.
In quantum systems, particles, for example, can exist in two different states at the same time.
For example, you could factor a very big number, one with 300 digits. It would take today's computers billions of years. A quantum computer might do it in hours. Zoller grew up in Austria and essentially taught himself physics.
I taught myself a lot of these things by just reading books, then I had to discover that there are physics journals. And reading physics journals and all of that, and then picking even a topic for my thesis for myself.
Cirac grew up in Spain and took a less direct route.
At the beginning, I never thought about becoming a physicist. I wanted to be an architect or an engineer or something. But later on, when I turned 18 and I went to university, I decided that I really wanted to understand well things, and this is why I decided to become a physicist.
While Wineland, who grew up in the U.S., took an even longer route.
Over a semester, I decided to be an English major, but I figured out, although I liked reading, and that wasn't my calling.
As theoretical physicists, Zoller and Cirac worked together exploring the theory and possible uses of quantum mechanics. They were inspired to explore quantum computing when they attended a conference organized by Wineland in 1994. There, a speaker offered the idea of using quantum mechanics to process information.
I remember that moment that we were talking to each other during the talk, saying, oh, we have to do that, we have to work on that.
We sort of pushed aside and said, oh, I think, listen to him. I mean, I think we can do that.
And I think this is where everything started.
So in this sense, it was really sort of a blueprint.
While Zoller and Cirac explored the theory, it was Wineland who took it into the lab.
We could immediately jump into this area and start to try to realize some of these ideas that they had put forth.
Because the laws of quantum physics mean particles can do two things at once, they can store more information.
So each of the bits, which are called quantum bits, qubits, now can be at the same time in 0 and 1. They can have 0, 0, 0, 0, at the same time 0, 0, 0, 1, at the same time 0, 0, 0, 1, 0. So you have all these possibilities living at the same time.
But actually making a quantum computer is still a work in progress.
We can talk in very exotic terms about what our ions are doing. The things that limit us are these actually very simple things. How do we control the power and also the frequency? That's certainly what occupies most of our time.
Will a quantum computer ever replace classical computers?
We're not going to do away with classical computers. We need classical computers to run our quantum computer.
But they agree it is coming.
Quantum computing per se is, in terms of computer science, kind of a new paradigm.
I believe that a quantum computer would be eventually built and it will work.
The 2010 Benjamin Franklin Medal in Physics is presented to J. Ignacio Cirac, David Wineland, and Peter Zoller for their theoretical proposal and experimental realization of the first device that performs elementary computer logic operations using the quantum properties of individual atoms.